So, welcome again. As you see, I'm changing settings every recording. This is really one of the lectures that I'm not a big fan of. I really, I'm really not a big fan of the topics of locking and stuff. So I have to break for much longer periods than I usually do when I'm talking about scheduling, for example. So let's get back to locking. A lock is just a variable basically that you must declare before you use, just like any other variable. In this case, you're basically using emiotics, and emiotics stands for mutual exclusion. And the lock variable, or just lock for short, basically holds the state of the lock at any instant in time. So this is basically where you store if the lock is acquired or if the lock is released. And then if the lock is available, okay, you can lock it. If it's not available, then you're just going to go in and sleep until it is available. And we'll talk a bit about how does this work. So you'll spin until you basically, and we say spin because it's sort of you're in an infinite while loop until the lock becomes available. So you do not actually check if the lock is available. You just do lock, try to lock, and if it's not available, you will not be able to acquire the lock. And basically you then go to the once you have the lock, you go into the critical section, and then you do whatever changes you're doing. And now this is an example where you're changing a variable that is probably integer, but then you might use it for example adding elements to a linked list or a double linked list or whatever that is. Okay. And basically, the way this is implemented, and we are going to go through this again in more details very shortly, is that you have two sort of two variables inside the struct of lock. So inside the definition of lock, you actually have two variables. One of them is sort of a linked list, a queue, which basically has all the different threads that are spinning, waiting for the lock to become available. And you will have another data structure that's a pointer to the thread which has the lock. So right now, if you look at struct lock t, you'll have a queue of waiting. That's basically a couple of threads, a few threads, 100, 10, 5, whatever. And you have p thread owner. Locking, by the way, is one of the things that people really have to take design decisions about, not just in operating systems, but also in programming languages. So Python, for example, for a very long time, they had one gigantic, enormous lock that would lock. I mean, multi-threading in Python was very tricky for a reason that the inventor of Python thought that, well, we need the single lock for things. You can read about it. So, but in general, it's a design decision that you take when you're designing your not just your operating system but also your programming language. And basically the information on what threads are waiting for the lock to acquire is hidden from the user. You cannot view it from the user side, but you have to be the kernel. I mean, of course, if you hack in the kernel, you can print that, but as a user, there is no way for you to actually know which threads are waiting for a certain lock. So the lock semantics, this is basically how the lock is implemented. So void lock, it does not return anything, and you take, I mean, the lock function takes basically a pointer to the lock that you created, just like here, for example, you have initialized the lock, and then you pointed the function, you passed the pointer to the function, and then while true, if there are no other threads that are holding the lock, if the lock is free, then the current thread acquires the lock, and the lock function will return. And when the current thread acquires the lock, you need to basically change the lock data structure to now point in the lock data structure that, like in struct lock t, you want to point to p thread owner, you want to point to the owner. If otherwise the lock is not available, queue the current thread, the one that is trying to call the lock in the waiting queue list, and put the thread in the blocked state. So we basically covered this without going through it. Okay, here's something that you might ask yourself about. Shouldn't this be an atomic operation? And yes, it should be. This does not look atomic because if you think of this, that the while loop, I mean, you can basically get descheduled. You can get removed from the processor right after you call the while move, and that would be pretty dangerous. Or you can basically get out from the processor, basically get evicted from the processor while during performing things in the while loop. Okay, so this doesn't look atomic. We will actually talk about how the hardware provides you with ways to make these atomic. Similarly, for unlocking, this is the logical implementation of how the unlock function is implemented. Where when unlock basically is called, it checks if the current thread is the owner of the lock, because maybe someone will just try to unlock a lock. So if you basically, if for example, let us basically go back to this code. Suppose that someone, instead of calling lock and mutex, calls unlock in the beginning, basically because he was basically writing in a hurry and forgot to put un, or basically so he calls unlock instead of lock in line 3. So this is why here you actually, the first thing you check is basically to make sure that you are the owner, the thread is the owner of that lock. If they're waiting threads, you then basically wake up all threads. Okay, you basically announce to all threads that that now this lock is available, and then all of these threads try to will wake up. Okay, and one of them, the first one to get to the lock, will be basically will gain the lock. So the first one to get to the lock will acquire the lock. Locks basically provide some minimal amount of control over scheduling to programmers. You as a programmer now can control basically some parts of your code such that you make sure that this is atomic. Okay, it although being the programmer, you are the person calling the lock and unlock functions. The scheduling is actually done, the management of this locking is done by the operating system. So this is another way for the programmer to influence how scheduling is done. You have to be very careful when you're using locks, because, well, yes, they do transform basically the chaos in scheduling to something that you can reason about. Still, you can actually do lots of harm using the locks and unlocks. You can turn your system into a really slow system. I mean, you can turn the fastest supercomputer to the slowest computer on Earth using locks. Okay. pthread locks is the name that the POSIX library uses for pthread locks is the POSIX library for locking. Okay, and mutex underscore t, pthread underscore mutex underscore t is basically the lock that is provided by the POSIX library for locking, and it's basically mutex is short for mutual exclusion between threads. Okay, and this is basically how you would actually write locking code. I hope you have read the previous chapter in the book. If not, do read it, because it's very important that you understand the lock APIs. Is it yeah, it's, I think, the previous one. Yes. Yeah, and you basically see that the POSIX version passes a variable to lock, which is basically it's basically the lock, the pointer to the lock. So This is very important because you might be using the library. Even a single thread might be in need of acquiring multiple locks at the same time. Think of it as, for example, your locking. Basically, the first lock is your basically door lock, your outside door lock. You might have another lock for your room, and you might have a safe in your room that has even a third lock where you keep like your most your most valuable stuff, right? So locking is quite similar. You might actually have multiple locks acquired by the same thread at the same time, because you want that thread to acquire, I mean, to, for example, add values of two different integers that are shared. So suppose that you have multiple shared data objects. Two of them are integers that you are going to basically take the two integers and add them. But since they are shared, then any other thread, if you're not locking both of them, any other thread might just change the value of one of them. And in that case, when you add them, you might get very different results based on scheduling. So you would want to basically acquire locks on these two on these two data objects.